A typical STATCOM configuration consists of multi-level VSCs based on IGBTs, phase reactors, and step-up transformer. It is shunt-connected to the grid. The reactive current is provided or absorbed by producing a controlled internal voltage waveform. Most STATCOMs available in the market today operate as grid-forming converters GFCs and require a grid voltage reference to operate with a defined level of grid strength. The voltage waveform is adjusted in its response with reference to the grid connection point voltage. In general, the STATCOMs operate as AC current-controlled device, although the control of the output current is achieved via the regulation of the STATCOM internal voltage behind the phase reactor in amplitude, whereas the angle is close to 90 degrees with respect to the grid connection point voltage. If the STATCOM voltage amplitude is higher than the system voltage amplitude, capacitive reactive power is provided to the grid. If, vice versa, current flows from the system to the STATCOM and inductive reactive power is provided. The amount of reactive current depends on the transformer short-circuit reactance and the voltage difference and is limited to the thermal limits of the IGBTs. In normal operation, I.E. the system voltage is within certain limits, both voltage amplitudes are equal and no reactive power is exchanged with the grid. An established control is if the grid voltage is above the threshold value, STATCOM control will decrease the amplitude of the STATCOM voltage waveform, making the STATCOM act as an inductive element and absorb reactive power from the grid. When the grid voltage is above the threshold value, the magnitude of the voltage waveform will be increased, making the STATCOM act as a capacitive element and providing reactive current to the grid. The main advantage of the STATCOM for improving transient stability lies in its ability to quickly control bus voltage. Specifically, the STATCOM can enhance power transfer during low voltage conditions, which are common during faults, thereby reducing the acceleration of local generators. Additionally, it helps mitigate the demagnetizing effects of faults on local generation. Unlike synchronous compensators, STATCOMs have no mechanical inertia, allowing them to respond much faster to changing system conditions. They do not contribute to short-circuit currents and have no moving parts. However, they possess a symmetric lead-lag capability and can theoretically switch from full lag to full lead within a fraction of a cycle. Numerous research papers have demonstrated the crucial role of energy storage systems (ESS) in power system control. By integrating an ESS with a STATCOM plus ESS, significant enhancements over traditional STATCOM performance can be achieved. Battery technologies offer advantages such as higher energy storage densities, greater cycling capabilities, improved reliability, and lower costs. This combined system effectively mitigates most stability and voltage fluctuation issues in the power system. A STATCOM, connected in shunt with the system, enhances transient stability by compensating reactive power at the point of common connection. The primary goal of applying reactive shunt compensation in a transmission system is to increase transmittable power during transients. This is accomplished by adjusting the power transfer capability in response to changes in the machine angle. Advantages in field of application: modern designs are modular and allow for a high level of scalability and flexibility, ensuring the total required dynamic and steady-state rating. Via the addition of shunt elements, the symmetrical output range of the pure STATCOM device can be adjusted to also meet non-symmetrical performance requirements. For conditions where a fast non-symmetrical dynamic range is required, on the one hand, thyristor-switched reactors and capacitors can be operated in parallel to form hybrid solutions. On the other hand, mechanically switched reactors and capacitors can be added to optimize slow response performance and provide additional steady-state capacity as required by e.g. typical intraday load flow changes. In a single line diagram of a STATCOM, if the DC capacitor voltage VDC is increased above its nominal value, the STATCOM operates in an overexcited capacitive mode, generating reactive power. Conversely, if the DC capacitor voltage is decreased below the nominal value, the STATCOM operates in an underexcited inductive mode, absorbing reactive power from the system. This behavior is analogous to adjusting the field voltage of a synchronous compensator. In power transmission and distribution systems, power electronics-based controllers are commonly referred to as flexible AC transmission system FACS devices. These FACS networks facilitate bulk power transfers, aiding in the construction of more transmission lines and power generation plants, thereby enabling neighboring utilities and regions to economically and reliably exchange power. Continuous advancements in power electronic technologies are enhancing the role of FACS devices within the bulk power system. This evolution is gradually transforming the electric utility industry into a more competitive market where power is traded as a commodity. Despite the potential benefits, transmission service providers are often hesitant to install FACS devices due to costs and the lack of systematic control. Utility providers need to implement local control measures to address various potential issues such as uneven power flow, transient instability, subsynchronous oscillations, and dynamic overvoltages and undervoltages. Among these, multi-level converter-based FACS devices offer improved power quality, reduced switching frequencies, decreased power losses, and minimized stress on individual power electronics components. Additionally, these devices enable more effective use of battery energy storage systems (BESS). An energy storage system (ESS) plays a crucial role in power system control, offering significant enhancements over traditional STATCOM performance. Recently, battery energy storage systems (BESS) combined with STATCOM have emerged as one of the most promising near-term storage technologies for power applications. Integrating an ESS with a STATCOM allows for the control of active power flow between the STATCOM and the point of common coupling (PCC). This enables the STATCOM to not only compensate reactive power but also store excess energy when generated power exceeds the limits that can be injected into the distribution grid. Additionally, this solution enhances control over power flow at the PCC by adjusting the direction of power injection, whether upwards or downwards. Without energy storage, FACS devices have limited flexibility and sustained effectiveness in supporting the power grid. Integrating an energy storage system (ESS) with FACS devices allows for independent real and reactive power absorption or injection into the grid. This integration results in a more economical and flexible power transmission controller. When a transmission line experiences intermittent power transfer variations, a FACS plus BESS combination can be used to regulate and adjust the power flow within the loaded transmission line. The superior performance of the combined FACS plus ESS system is likely to be more appealing to transmission service providers. Power system deregulation, along with transmission limitations and generation shortages, has altered grid conditions, creating scenarios where energy storage technology plays a crucial role in maintaining system reliability and power quality. Energy storage devices offer multiple benefits, such as rapidly damping oscillations, responding to sudden load transients, and continuing to supply power during transmission or distribution interruptions. Additionally, these systems can correct load voltage profiles through rapid reactive power control, allowing generators to balance with the system load at their normal speed. Figure illustrates the typical architecture of a STATCOM connected with an ESS to an electric utility system. The static synchronous compensator STATCOM is a shunt-connected, power electronic converter-based FACS device. Unlike the static VAR compensator SVC, the STATCOM does not use capacitor or reactor banks to produce reactive power. A major disadvantage of a traditional STATCOM without energy storage is its limited steady-state operating modes, which are either inductive lagging or capacitive leading. Although the traditional STATCOM can control both output voltage magnitude and phase angle, these cannot be independently adjusted in steady state due to the lack of significant active power capability. Typically, the STATCOM converter voltage is maintained in phase with the PCC voltage, ensuring that only reactive power flows from the STATCOM to the system. However, due to losses in the coupling transformer and converter, the converter voltage is generally maintained with a small phase shift relative to the PCC voltage, allowing a small amount of real power to flow from the PCC to the DC bus to compensate for losses. The real power capability of the STATCOM is very limited due to the absence of energy storage on the DC bus. Compared to the traditional STATCOM, the STATCOM plus BESS offers greater flexibility. The number of steady-state operating modes is extended to include inductive mode with DC charge and discharge, and capacitive mode with DC charge and discharge. Thus, the STATCOM plus BESS can operate at any point within the steady-state characteristic circle. Depending on the energy output of the battery or other ESS, the discharge charge profile is generally sufficient to stabilize power regulation in the system and maintain operation until other long-term energy sources are activated. Figures show the architecture of connecting BESS with STATCOM and the control architecture. One drawback of FACS plus ESS is that the size of the storage systems, particularly battery energy storage BESS, may be too large for practical use in large-scale transmission-level applications. Large battery systems can sometimes exhibit voltage instability when numerous cells are placed in series. However, even large oscillations can typically be mitigated with modest power injection from a storage system. The ability to independently control both active and reactive power in STATCOM plus BESS makes them ideal controllers for various power regulation applications, including voltage fluctuation mitigation and oscillation damping. The most important use of the STATCOM plus BESS is to stabilize disturbances in the power system. STATCOMs with energy storage offer numerous advantages for power system operation and control. These applications include reactive and active power control, stability enhancement, system security improvement, integration of renewable generation, avoiding new transmission line construction, managing power flow congestion, and providing control mechanisms for remedial action schemes. Wind power generation, a key renewable energy source, requires control due to its inherent intermittency. Power electronic interfaces have proven essential in integrating renewable energy. With high wind power penetration into the grid, maintaining power quality and continuous long-term operation of wind generators becomes crucial. The pulsating nature of wind turbine torque produces oscillatory active and reactive power outputs at blade passing frequencies, worsening power quality at the PCC and potentially damaging connected generators. During severe disturbances, such as line sag or faults, turbines transmit less power to the grid, causing an imbalance between mechanical and electrical power, which increases turbine speed. This speed increase leads to higher reactive power consumption and voltage dips. Stability can only be maintained if the increased generator speed remains below the critical limit, necessitating external reactive power supply during faults. As wind power generation increases, wind systems must support the grid during faults rather than disconnecting. Consequently, many countries are developing grid code requirements for fault ride-through capabilities in wind power systems. Using a battery in parallel with a wind turbine allows for maximum power production and storage of excess energy that cannot be injected into the grid. A battery connected to a STATCOM is an optimal solution for maximizing power injection in weak networks within distributed generator DG systems. The generator can be sized to produce more power than the maximum capacity, with the excess absorbed by the battery. In cases where this situation is possible but not probable, the BESS can act as a dump load to absorb the excess power. STATCOMs can enhance stability even in offshore wind farms, which are often weakly connected. When distributed generation DG power exceeds the maximum that can be injected into the power system, the battery absorbs the surplus. Conversely, if power consumption is high, the battery supplies the necessary power. If the battery is fully charged, a dump load can absorb the excess power, while excessive consumption can only be managed by limiting power. STATCOMs with storage also provide low-voltage ride-through capability and reactive power compensation. There are numerous examples of using STATCOMs with storage for stability enhancement. Generally, BESS units are designed and installed for load leveling, stabilization, and load frequency control. The optimal installation site and capacity of BESS depend on the specific application and power system requirements, and this is widely implemented for load leveling purposes. Integrating battery energy storage with a FACS power flow controller improves power system operation, regulation, and control. Due to the intermittent nature of wind, the active power generated by wind power generators fluctuates, which in turn causes fluctuations in the reactive power absorbed by the wind power generator unit. After a disturbance, low-frequency oscillations in the AC system can be damped by injecting or absorbing real or reactive power. In some cases, the reactive power injected into the system depends on the STATCOM terminal voltage, while the ESS adjusts according to variations in real power flow. Damping power oscillations with real power is more effective than using reactive power, as it does not compromise the system's voltage quality. In practical scenarios, connecting an ESS to the AC system provides better dynamic performance for damping oscillations when using a series-connected voltage source inverter static synchronous series compensator compared to a shunt-connected inverter. However, this is often impractical due to the additional costs involved. The pulsating torque at blade passing frequencies causes variations in the slip of the wind power generator around its normal operating point, significantly affecting the turbine's terminal voltage. This variation is also influenced by the active power output of the wind turbine, causing changes in voltage drop across the distribution circuit. The voltage drop can be divided into horizontal and vertical components, corresponding to the in-phase and quadrature components of the grid impedance voltage, respectively. In summary, a STATCOM plus BESS unit can be used for load leveling, saving energy during peak demand, minimizing subsynchronous oscillations, and enhancing transient and dynamic stability. Another advantage of using STATCOM plus BESS is the significant reduction in the required DC-linked capacitor value. For certain applications, a small capacitor is sufficient to smooth the battery DC current, which is a notable benefit of integrating a battery energy storage system BESS with STATCOM. The cost of an integrated system can be divided into three main segments: the energy storage system, supporting systems such as refrigeration for SMEs, and the power conversion system. The cost of the energy storage system is primarily determined by the amount of energy to be stored. For high-power, low-energy storage applications, the configuration and size of the power conversion system may become the dominant cost factor. To establish a realistic cost estimate, the following steps should be considered. Identify the system issues to be addressed. Study preliminary system characteristics. Define basic requirements for energy storage, power, voltage, and current. Determine the utility's financial benefits from system integration to assess the return on investment. Model system performance in response to demands to evaluate the effectiveness of the BESS. Optimize integrated system specifications and determine the overall system cost. Study and compare the performance and costs of various energy storage systems. SVC versus STATCOM. SVC static VAR compensator and STATCOM static synchronous compensator are both devices used in power systems to regulate voltage and improve power quality. The main difference lies in their operation, control method. SVC uses thyristors to control reactive power by varying the impedance of the connected equipment, usually a reactor or capacitor. STATCOM uses power electronics, usually voltage source converters, to inject or absorb reactive power continuously, providing faster response and better control. Response time. SVC typically has a slower response time compared to STATCOM due to the nature of thyristor-based control. STATCOM can respond much faster to changes in the system, offering more dynamic voltage support. Topology. SVC is usually a shunt-connected device, meaning it is connected in parallel with the power system. STATCOM can be both shunt-connected or series-connected, depending on the application requirements. Voltage support. While both devices provide voltage support and reactive power compensation, STATCOMs offer more precise and dynamic voltage control capabilities. In summary, while both SVC and STATCOM serve similar purposes in power systems, STATCOMs offer faster response times, more precise control, and greater flexibility in voltage support compared to SVCs. In the domain of power transmission and distribution, the integration of renewable energy sources has prompted the development of more sophisticated grid stabilization technologies. One such advancement is the Enhanced Static Synchronous Compensator or E-Statcom, a complex electrical installation in the transmission system operator TSO power grid to compensate for short-term load fluctuations and provide the grid with inertial response by employing energy storage systems to absorb and supply short bursts of high active power. Features of E-Statcom: fast voltage frequency support, synthetic inertia, fault current generation, system strength support capabilities, grid forming control, scalable energy storage capacity in the hundreds of MWs. E-Statcom installations are substantial in size, even spanning the equivalent of a football field. Alongside the energy storage unit, E-Statcoms incorporate various components such as high-voltage AC transformers, AC-DC converters, AC circuit breakers, disconnectors, earthing switches, instrument transformers, control rooms, protection and monitoring systems. They also accommodate auxiliary systems like cooling devices. STATCOM operation. Basic principle of operation. In the case of two AC sources, which have the same frequency and are connected through a series reactance, the power flows will be reactive power flows from the higher to the lower voltage magnitude source. Consequently, the phase angle difference between the sources decides the active power flow, while the voltage magnitude difference between the sources determines the reactive power flow. Based on this principle, a STATCOM can be used to regulate the reactive power flow by changing the output voltage of the voltage source converter with respect to the system voltage. Modes of operation. The STATCOM can be operated in two different modes. Voltage regulation. The static synchronous compensator regulates voltage at its connection point by controlling the amount of reactive power that is absorbed from or injected into the power system through a voltage source converter. In steady-state operation, the voltage V2 generated by the VSC through the DC capacitor is in phase with the system voltage V1 delta equals 0, so that only reactive power Q is flowing P equals 0.1. When system voltage is high, the STATCOM will absorb reactive power inductive behavior. When system voltage is low, the STATCOM will generate and inject reactive power into the system capacitive. Subsequently, the amount of reactive power flow is given by the equation. VAR control. In this mode, the STATCOM reactive power output is kept constant independent of other system parameter. Compares the proposed damping controller with conventional pre-type damper under the same gain parameter. As can be seen from the black arrow, the oscillation of proposed strategy is less than that of conventional method, indicating the superiority of proposed strategy.